Hello students, welcome back to CLARI Concepts, Unleashing Conceptual Learning. Visit our website clariconcepts.com to get more insights on conceptual lectures. Today is very interesting lecture and I want you to see till the end, okay, because you are going to learn a new law altogether. So let me begin this session with one of the question. Have you ever thought why dams are broader at the bottom and narrower at the top? Have you looked at the guidelines of this smart band, band watch by smart band? You can see in the guidelines that they say that they are not advisable to use for deep diving. It has certain depth limitations, right? So they say that it is water resistance up to, let's say, 50 meters of depth, beyond which there are chances water can penetrate into this watch, this band, right? So why it has depth limitations? So the answer to both of these questions can be provided by a law called hydrostatic law. So today in this lecture, we are going to learn about what is hydrostatic law and why is it that the case when the band comes with the depth limitations and also the dams are broader at the bottom and narrower at the top, right? So let us get into this. So let's say, for example, if I talk about hydrostatic law, basically it deals with the variation of pressure along vertical directions, mainly in a fluid at rest. See, again I am saying hydrostatic law deals with pressure variation in a fluid at rest along the vertical direction. So whenever a fluid is at rest, a large fluid body is at rest, and what happens to the pressure when you move down or when you move up. Okay, so pressure variation and its behavior in vertical direction is basically explained by hydrostatic law. So let us understand that, let us suppose on one sunny day you went to a swimming pool and you jump from certain height, and let's suppose at one instant I have taken a photograph, and at that particular instant you are at the depth of Z1 meters from the free surface of water, and the pressure, fluid pressure felt by your nose at this particular depth, let's say it is P1 Pascal. For example, imagine yourself going into the swimming pool and at depth Z1 your pressure felt by your nose is P1 because of the water around your nose, right? And again you move down, and let's say at depth Z2 meters from the free surface, again pressure felt by your nose is some P2 Pascal. Now if I ask you the question that whether, if you talk about value of P2 and P1, at which one of them will be higher? I mean, which one of them will be smaller or higher? So let's say, for example, whether the pressure felt by your nose at Z2 depth, that is P2, will it be higher than P1? First option. Will it be smaller than P1? Or will it be equal? What is your intuition saying it to you? You think about it. I am 100% sure your intuition will give you the correct answer. Yes, I would say that when you do this experiment by your own or take a pressure gauge with your hand, and you will see that the pressure at a larger depth felt by your nose will be higher in comparison to pressure at the lower depth. Now we have understood that pressure will be higher at the lower depth, pressure will be lower at the lower depth. I mean higher at the higher depth and lower at the lower depth. But how much higher? That is a big question. Now see, so let us suppose P2 is larger than P1, but my question is what extent, till what extent there is a difference between the P2 and P1. So now this will be answered by the hydrostatic law. So let me take one cylindrical fluid element. So this is cylindrical fluid element which has a circular area of capital A meter square. This is basically a fluid element itself. A fluid element itself within the pool of water, right? It's a water element only, but I'm just marking it as a cylindrical element. Now, the height of the element is, let's say, h meters, right? That means the distance between Z2 and Z1 is h meters. And this fluid body is basically at rest. That means it is in equilibrium. So if fluid body is in equilibrium, that means the element of this water body is also in equilibrium. And when element is in equilibrium, I can say that the summation of the forces acting on this element in vertical direction should be equal to 0. Again, the summation of all the forces acting on this element in vertical direction should be equal to 0, right? See, also I can say summation of forces along horizontal direction should also be equal to 0. But right now, because I am worried about vertical direction, I will only consider that as a case. Now, when I want to do the summation of all the forces, firstly I need to know what are the forces acting on this element along vertical directions. For that, I will have to dissolve the forces in two different categories. One is surface forces other is body forces. So try to introspect this particular element and try to see what are the surface forces acting on this element and what are the body forces acting on this element, and from those forces which of them are in vertical directions. So let us begin with surface forces. So this body has basically three surfaces, one the top surface, circular surface, one bottom circular surface, and one this cylindrical surface, right? Now surface forces on this body basically are because of pressures. Pressure will always act normal to the surface, right? So if I have a cylindrical body, pressure will always act normal to the surface, from top, from bottom. Now from this body has three surfaces, as I said. So from all these three surfaces, I am least bothered about the circular surface. Why? Cylindrical surface. Why? Because the cylindrical surface, all the pressures are along horizontal direction. You see, this body, the pressure forces are along horizontal direction, and all of them will balance each other. And I am talking about the force in vertical. So all this force will never be a part of my equation. So from these three surfaces, there are only two surfaces which come into picture when I talk about the pressure. So top surface, which has the force in downward direction, and the bottom surface, which has the surface force in upward direction, right? So I would say the force on top surface will be, let's say, F1. And what is F1? It will be pressure at this surface. So if pressure at depth Z1 is P1, so P1 into area will be the value of force, F1, right? Similarly, the pressure, force from the bottom, that is F2, will be equal to pressure at that particular face into that circular area. So P2 into area A is the pressure at the, is the force value at the bottom face. Yes, these two are the surface forces we have considered. Now let us talk about the body force. Body force basically is the weight of the fluid itself, the weight itself of the fluid, which is always acting in the downward direction. So W is the weight, and if I talk about W, W will be mass of this element into G, gravitational acceleration. Now what is mass of the element? It is density of the element, fluid multiplied by the volume of the element. So density into volume will be your mass, and G will be as it is. Why? Because density is mass by volume, so mass is density into volume. So I have replaced mass with rho and V, where rho is density of the water and V is the volume of the cylindrical element. Now can I say volume of this element is cross-sectional area A multiplied by the perpendicular distance H? Yes. Therefore, you can say V is area into H, and therefore W is rho A H G. So you just take it left side. So now what you will be doing is you are trying to solve the equilibrium equation for these three forces, 1, 2 and 3. So let us resolve this, and we will first take our sign convention that Y is positive upwards. So all the forces in upward direction will be positive and the forces in downward direction will be negative. So from these three forces, F1 is downward, W is downward, F2 is upward. So I will take F2 as positive, F1 and W as negative. So F2 minus W minus F1 should be equal to 0. And you take both these on the right hand side, you will get F2 equals to W plus F1. Now substitute the values. F2 is P2 into A. So put the value. W is rho A GH, rho A HG or GH. F1 is P1 into A. You put this. Now you see, you can take area common and out, right? And then you can cancel area from both the sides. So P2 is equals to rho GH plus P1, and you can just swap these terms. P2 equals to P1 plus rho GH. Now I hope you are coming to a point. What is P2? P2 is the pressure felt by your nose at a depth of Z2. That means pressure within the fluid at depth Z2. What is P1? P1 is pressure in the fluid at depth Z1. What is rho GH? You can see this equation. P2 is equals to P1 plus rho GH. It means the pressure at P2 is rho GH, is larger than P1 by the amount rho GH. Yes. So where you can see that this question is now solved. We said that how much larger? So it is larger by the amount called rho GH. Now what is rho GH? Where rho is density of the fluid which was filled between these 2 points, because we have taken cylindrical element between these 2 points, right? And rho was the density of that particular cylindrical element. So rho will be density of the fluid filled between these 2 points. Yes. What is G? Gravitational acceleration, with the value is 9.81 meter per second square. And what is H? H is the distance between Z1 and Z2, the vertical distance always, right? So now if I simply write in generalized form, just removing 1 and 2, what you can say, pressure, so what 2 is the point at lower altitude and 1 is the point at higher altitude. Higher altitude means the this is height, right? So pressure at lower altitude point will always be equal to pressure at higher altitude point plus rho gh. Always. Pressure at low altitude point will be equal to pressure at high altitude point plus rho gh. Always. Okay. So this basically is the general form of hydrostatic law, and mostly this is valid for the incompressible fluids. Okay. So if I give you some example, let's say I have a point A in a fluid where the pressure at depth of Z1 and the pressure at point A is 1000 Pascal. This 1000 Pascal is, let's say, gauge, for example, gauge pressure. And I have a point B which is at the depth of 2 meters from point A. And if I ask you to find out pressure at point B, can you find out? Yes, obviously, because this fluid is at rest. First of all, I know the pressure at point A, which is 2 meter above pressure at 2 meter above the point B. So if you know pressure at any point above this point B, and if you know the distance between these 2 points, you can easily find out the pressure at point B by using hydrostatic law. How? Pressure at low altitude point equals to pressure at high altitude point plus rho gh. The same equation. So pressure at B will be equal to pressure at A plus rho gh, where rho is density of the water. So PA is 1000, rho is 1000 because it is water, G is 9.81 and H is 2 meter because distance between A and B, and you calculate the value. This is 20620 Pascal. So pressure at B is this much. Now let us take another point C, which is around 3 meters from point B, and you find out the pressure at point C. You will again use the same formula, PC equals to PB plus rho gh. So PB, you know, rho is 1000, G is 9.81 and H is 3 meters. You put the values and get the answer. You will get 50050 Pascals. Now if you look at these pressures, you will see that the pressure is increasing 1000, 20,000, 50,000. So as you go deeper and deeper, the pressure increases, right? And therefore the the hydrostatic law says that the rate of increase in pressure with respect to the depth in a fluid at rest. See, the rate of increase in pressure with respect to the depth in a fluid at rest is equivalent to the specific weight of the fluid. This is the generalized statement of hydrostatic law, which is valid for compressible as well as incompressible flow. So how you can write this in mathematical equation? It is dP by dz equals to rho g. dP by dz equals to rho g. Now you see, what is dP by dz? It is delta P by delta z. Simple. It is the rate of increase in pressure, right? What is rho g? It is specific weight. Simple. Rho is density, g is gravitational acceleration. So we know that gamma, which is specific weight of the water, is rho into g basically, right? So now what was that? P2 equals to P1 plus rho gh. If you take P1 on the left hand side, you will get P2 minus P1 equals to rho gh. So P2 minus P1 is delta P or dP, and then rho g and h was delta z. So you can take delta z on the denominator, you will get dP by dh equals to rho g. So you can get basically that equation of incompressible fluid hydrostatic law from this only, right? So this is generalized form. So I hope now you got an answer that why are dams broader at the bottom. You see, because on the reservoir side, as you move down, the pressure is going to increase continuously, and in order to make this dam safer in design, this section has to withstand the larger forces over here, and this can only be withstand because when you have the larger broader depth, broader section at the bottom and narrower at the top. Also now I hope you have understood this answer, that why has bands come with the depth limitations, because beyond 50 meters the pressure of the water is, because when you go in deeper and deeper in the water, pressure is going to increase continuously, and when pressure increases continuously, there will be a point beyond certain depth where your ceilings, whatever waterproofing element that these people have kept in the bands will no more be useful and water may penetrate into the device, right? Therefore they say that it can only be water resistant, not waterproof, right? There is a difference. Water resistance means it can resist water up to certain limitation. Waterproof meaning it can never, it is basically waterproof means at any depth it can work, kind of thing, right? So I hope you understood this particular concept, and see you soon in the next class. For such conceptual videos and other subjects, you can log into our website www.clariconcepts.com. Thank you so much.